Now maybe. Okay, so over to you, Silvia.
Okay, so thanks a lot to Aiden and to organizers for asking me to give this talk today, and also for asking me to talk about this specific work that I've been doing with Jorge Urchan here in Paris, that has a bit of a different framework to the standard kind of many-body dynamics that we're interested in. So why I'm saying so, well, the main goal and the main motivation might be familiar to some of you. So what we're interested in is to understand this quantum bounds that have attracted a lot of attention in the past years, and they're basically bounds on a set of transport coefficients such as the viscosity or the conductivity, and on chaos quantifiers such as the Lyapunov exponent. And I'm going to tell you more specifically, in particular, how to define this quantum Lyapunov exponent, but just tell me why it has attracted a lot of interest. Is basically because all these kind of bounds, they're saturated by models of black holes, and in particular such the Vieky-Tayev model, which is an analog of a black hole. And for this reason, they have attracted a lot of attention, initially only in high energy physics and then in condensed matter. And what our goal, or somehow what we have been interested in since I started my postdoc, is to try to understand what are the physical mechanisms beyond these bounds, and what are the properties of the system that saturate them beyond black holes. So what we consider are these, what I'm calling here quantum models. So basically it's free dynamics of particles on top of curved manifolds. And I'm going to tell you why we consider them, why we believe they do have an interesting dynamics, and something to tell us also about many body systems. So this is basically the outline of the talk, given this simple motivation. So I'm going to tell you a bit more, what are these quantum bounds, in particular the one on the Lyapunov exponent. Then I'm going to motivate why we believe these free dynamics on curved manifolds are interesting. And then somehow the first part of the result concern general scaling properties of this class of systems. So what are the relevant length scales at work? And I will show you that on top of these systems, these bounds that we're interested in are violated. And this is why they're particularly relevant to be studied, to see how quantum mechanics somehow enters the game and implements the bound in practice. So I'm then going to illustrate the mechanisms that we identified somehow are implementing the bound. In particular, I'm going to focus on the pseudosphere, which is a simple two-dimensional surface with constant negative curvature. Okay, so let's start from these quantum bounds, and in particular from the Lyapunov exponent. And let me start from the classical definition. So classically, chaos is defined from the instability of trajectories to respect to small displacement in the initial conditions. So imagine you have a trajectory and you make a small displacement of the initial condition, then the system is chaotic if the distance between the two grows exponentially fast with a rate which is defined as the classical Lyapunov exponent. So this can be formalized a bit better, but loosely speaking, if the derivative of the trajectory to respect to the initial condition grows exponentially, then the rate is called the Lyapunov exponent. And by recalling how Poisson brackets read, basically this derivative of the trajectory can be rewritten as the Poisson bracket between the trajectory at time t and the coordinate at time 0. And now understanding how to generalize this concept in the quantum domain has attracted a lot of attention, I would say, since the beginning of quantum mechanics. And today I'm going rather to focus on a specific object, which is the square commutator that was introduced by Lyapunov-Chinnikov. And the reason for this is particularly simple. If instead of A, you take X at time t, and instead of B, you take the position at time 0, well, you see that in the classical limit, this object, the commutator becomes a Poisson bracket, so this object is expected to grow exponentially fast in the presence of an underlying chaotic classical limit, is expected to grow exponentially fast, which a rate which is given by twice the classical Lyapunov exponent. And this is true at least at short times before what in jargon is called the Ehrenfest time, or the scrambling time, which is proportional to the logarithm of the inverse of the Planck constant. So there is this somehow this regime, this Lyapunov regime, where I can see exponential growth. And now if you expand this kind of object, this square commutator, you will see that there are correlation functions which have an unusual time ordering, and they have been called out of time order correlators. And I would say they've attracted a lot of attention since Kitaev in 2015 suggested to use them as a probe of chaos also in the many-body case. And from that moment, I believe also in this series of talks, you've heard about this OTOC several times. Now, let me remark something, is that such an exponential growth to be appreciated really needs a separation of time scale. So in quantum systems, you really need to have a large Ehrenfest time in order to appreciate an exponential growth. And this will not be present, for instance, for quantum spin chains where h bar is equal to 1. So in that case, we cannot expect any Lyapunov exponent. This is really associated to some sort of, to the presence of some effective Planck constant, which can also be like 1/n in systems like the SYK, which has all-to-all interaction. So given this somehow intrinsic semi-classical nature of the Lyapunov exponent, it might come as a surprise the fact that actually quantum mechanics imposes a bound on the value that it can attain. And this was proved in this famous paper of Maldacena, Schenker, and Stanford in 2016, which proved that if you take an OTOC and you compute it for a thermal density matrix, and in particular they consider a regulated version of it, well, the exponent, so the rate coming from the OTOC of that OTOC shall be bounded by 2 pi and the temperature over h bar. Now, this bound, the bound to chaos, which is by the low temperature, is basically a bound on a time scale because the Lyapunov exponent is the inverse of time, and it concerns somehow this what's called the Planckian time, a Planckian time, which is the ratio of T, so the temperature over the Planck constant. And now this Planckian time scale was actually identified in a discussion of different kind of bounds related to anomalous transport behavior of a large class of different materials at low temperature. So on one side, there has been a large discussion about unusual linear T resistivity that concerns a very large class of materials, or also actually the original discussion of Planckian transport incorporates drew an implicit parallel with a lower bound on the shear viscosity, which I'm showing here, that bounds basically the shear viscosity over the entropy density with h bar over 4 pi. And this was originally identified in relativistic plasmas. Now, as far as I understand, and I'm not an expert on this topic, there is no exact consensus on the status of the bound on transport. However, they have seemed to be consistent, so they've been proposed to be consistent with some conjectured Planckian bound, which constrain the smallest physical timescales in the problem. So what's also remarked is that basically this Planckian timescale characterizes all the models that are saturating these bounds. So concerning these two different sets of bounds, there has been, as I was telling you, a lot of attention recently, but there are many open questions. So for instance, the relation between the two, or what are the properties of systems that saturate them, and what we have been interested in, as I told you, is trying to understand if such bound exists. They should not concern somehow black hole physics, but they should be limitations imposed by quantum mechanics, and we would like to understand them, or at least to get physical intuitions on what are these quantum effects that are inducing these bounds. And so to do this, let me tell you. So we try somehow to simplify the model as much as possible, really to pinpoint somehow what are these effects. So why are we interested in dynamics on curved manifolds? So first of all, we want the bound to be effective. So we need h bar over t over the temperature to be finite, and this may only be achieved in the semi-classical limit for very low temperatures, which correspond to the lowest classical energies of the system. So one can start by taking an Hamiltonian in the classical limit for h bar, for small h bar. And what's clear is that if the potential has an isolated minima, then there is no chaos at low energies, in the sense that the system will basically sit on the classical ground state and will just perform vibrations in the quantum fluctuations around it. On the other hand, if one needs a potential such that the manifold of the minima of the ground state has dimension greater than 2, such that even if I go at the lowest energies, there will be long distance motion somehow at the bottom of the well, so quantum fluctuations will be non-harmonic and chaotic. And this is the situation that we are looking at, that one would be interested in. So with this in mind, there are two natural choices for non-trivial dynamics up to the lowest temperatures, and one of these is basically free propagation bounded by walls, which are billiards, and free dynamics on curved manifolds. And billiards and manifolds actually share a scale invariance property, meaning that configurations in the configuration space, once identify an initial condition, all the trajectories that will be on the same geodesic, and changing energies just amount in rescaling the velocity. So independently on the velocity, I will be always on the same trajectory, and the different energy will just rescale my velocity. And now, when we compare the two, actually, it was discussed in one of the appendices of the Arnold book on classical mechanics, that actually billiards can be seen as a deflated limit as a particular case of a manifold, in which basically we're taking one of the directions and we're sending it to 0. So for instance, an ellipsoid in the deflated limit becomes an ellipsoid billiard, and so on and so forth. And for instance, holes in billiards can be associated to regions of negative curvature in the associated model. And this is true at the classical level and also at the quantum level. So there is a mapping basically between these two. And for this reason, we choose to focus only on manifolds, because they encapsulate also billiards. Okay, now before getting into some more details, let me tell you some of the motivations for some further motivation. So we're not interested, so this is not just an abstract construction, an abstract study, but actually our main motivation and actually goal for future study is to see and to study many body systems. And what I would like to mention is that actually these results also have applications, have potentially applications for macroscopic systems. So in fact, one can think about her spheres as a macroscopic billiard. In fact, in phase space, a system of n Hart spheres can be seen as a point moving freely inside a region bounded by the non-overlap condition for the spheres. So it's a 3n dimensional billiard. And at the same time, also spin liquids can be pictured as macroscopic manifolds. In fact, specific kind of classical spin liquids have a highly degenerate manifold of ground states, and if you combine this with the condition that spins have to be constrained to have a fixed norm, this defines a macroscopic manifold. And in particular, as we will see, the scaling that is coming from manifolds was actually the scaling for the Lyapunov was actually identified in a classical spin liquid. But I'm going back to this later. So this was just to somehow give some further motivation for what's our final goal, but not in this talk. So now that we have identified which kind of system we want to look at, let me tell you what are their properties and why they do violate the bounds. So let me start with the definition of manifolds. So what we look at is a Riemannian manifold parameterized by a set of coordinates xi and a metric tensor jij in n dimensions. And from now onward, it's going to be convenient to rescale everything. So to see what are the scales playing a role in these models. And in particular, I'm going to rescale everything by a characteristic length, which I'm calling a big R of the problem. And for the classical Hamiltonian dynamics, the classical Hamiltonian has this form where now P, G, both the momentum and the metric tensor are dimensionless variables. And now in this kind of systems, basically in the absence of any potential, trajectories are geodesics. And as I told you, all the trajectories with the same coordinates will go on the same geodesic, just at different velocities. Now, in the study of the quantum case, we shall look at the Schrödinger equation, of course, where the Hamiltonian is given by the invariant Laplace Beltrami operator, which is just basically which is the Laplacian on curved space. So it has this expression. It's basically related to the derivatives with respect to the coordinates, and one also has to derivate the inverse of the metric tensor. And here with small g, this is just the determinant of the metric, and this might look a bit ugly, but one just has to think about the Laplace operator in spherical coordinates that we know very well when we solve the radial equation with the angular momentum. So now the quantum nature of the particle is going to be accounted. So the scale that enters into the game is the thermal de Broglie length. And in particular, this vanishes in the classical limit or for very high temperatures. And indeed, what I'm going to tell you is that quantum effect become dominant when this length scale becomes of the same order of the characteristic geometric length of the problem. The first result basically comes from some dimensional analysis. So let me start from an operator in the Heisenberg representation, and I can just rewrite the Hamiltonian in terms of H bar and the length scale. And now the Laplace Beltrami will only depend on dimensionless variables. And I also can multiply and divide by the Planck constant and basically by the Planckian time. And basically I find the following expression where I see that the intrinsic characteristic time scale for this class of problems is really the Planckian time. So it's given by H bar over the temperature. And the second thing that we find from this simple rescaling is that when I compute observables in units of t over the Planckian time, the dimensionless variables will going to be only a function of the ratio between the characteristic geometric length and the Broglie length scale. So let me show you what I mean. So if, for instance, I'm looking at the Lyapunov exponent, so I take the square commutator, and then I assume that this is going to grow exponentially fast in time. I multiply and divide by the Planckian time. So here I get the dimensionless Lyapunov exponent, the one that should be bounded by pi. And because of this, I can immediately say that it's going to be only a function of R, so this length over the thermal de Broglie length. And the same, of course, is true also for transport coefficients, which can be computed from two-point functions, thanks to Kubo theory. And also in the case of the viscosity, if you take and rescale things appropriately, we also find that this is only a function of this R over the thermal de Broglie length. So what this means is basically if I'm looking at the rescale dimensionless Lyapunov exponent, so this H bar lambda over T, actually what I have to think about is on the x-axis to put this ratio between this length scale. And what the bound of Maldacena-Schenker and Stanford is telling me is that basically this quantity has to be smaller than this pi. So now what we want to see is what can I say on this kind of the plot where I know that the classical limit shall be valid. So when the thermal de Broglie length is much bigger than, is much smaller than everything else. So when each bar basically is going to 0. So what we will find is what we can find is actually that we have an expression that will violate the bound. So how do I find, for instance, in the case, this is standard calculation in the case of Lyapunov exponent. So I go in the classical limit, and on manifolds, actually all chaos is coming from the geometry. So the right way to identify a Lyapunov exponent is to take the distance between two geodesics and see how they separate with the length, path length, and this will grow exponentially fast, where R is this characteristic path length that is identified on chaotic manifolds. And now we can use the fact that the trajectories are geodesics, which have a velocity that only depends on the energy. And now I use the equipartition theorem. So instead of the energy E, I can substitute T, the temperature. Here I'm considering 1 degree of freedom, but this can be done appropriately in the large for every system size, so for n degrees of freedom. And now from these two, I can write the classical Lyapunov exponent, which is in units of time, as a velocity over this characteristic path length, and immediately obtain that the characteristic, the classical Lyapunov exponent shall be square root of temperature. So if now I divide it by temperature, we find this 1 over square root of T that I'm plotting here. So basically what I'm saying is that at very large temperatures, or at the, for classical limit, in h bar going to 0, this goes as 1 over square root of T, but as I approach as the length become of the same order of the system size of this geometric length scale, I'm going to violate the bound. And what happens is that violation of the bound occurs exactly when the two length scales are of the same order. So this somehow identifies the length scale at which quantum effects become dominant. And what I would like to do from now on is try to see how quantum mechanics intervenes at this length scale to implement the bound in practice. So now before going to our try model, so let me tell you something that I mentioned you before about the scaling of the Lyapunov exponent with the square root of temperature. So this was indeed reported in a many-body system, and in particular in this paper by Biteyevsky, Bhattacharya, and Mössner in 2018, in which they studied a classical spin liquid. So in particular, an antiferromagnetic or 3 Heisenberg spins on the Kagome lattice, in which there is all-to-all interaction inside each hexagon. So at t equal to 0, this is a classical Z2 spin liquid, in the sense that there is a macroscopic, the general ground state, identified by the fact that the global spin on each plaquette has to be 0. And indeed, so in this case, I guess there is chaos up to 0 temperature, in the sense that there is this macroscopic ground state and absence of order. And indeed, what they found by looking at the classical Lyapunov exponent was that the Lyapunov exponent grows with square root of T. So, which is exactly what comes out from simple dimensional analysis on manifolds. So this is just to say that this is not completely abstract, but it has important consequences on many-body systems. So now that we have identified this classical violation, of course, we want to know how quantum effects are coming in the game. And this brings me to somehow the main bulk of the talk, which is seeing these quantum effects on a simple time model, which is the pseudosphere. So what we do is basically we identify 3 kinds of quantum effects that can happen. So the first one is somehow the most trivial one, and it basically says that the quantum fluctuations are dominant when the thermal de Broglie length is of the order of the system size. This is really, maybe shouldn't even be here, but basically when the thermal de Broglie length is of the same order, I cannot even make any semi-classical approximation. So I'm the bound is active, but just because I have a small, I only have a few levels, and it's not interesting. Or the classical case is that if I consider a spin-S system with a very small system with a very small spin. So in this case, the quantum effects are basically trivial, and I don't even have all this description. Now, to identify somehow a more interesting mechanism, I'm going to introduce you this time model, which is constructed starting from the pseudosphere, which is the surface of the constant negative curvature. And it's called pseudosphere in analogy with the standard sphere, which has a positive curvature 1 over r square. Now, the reason of this choice is that actually free motion on compact surfaces of constant negative curvature is the most chaotic as possible, and its classical and quantum chaotic character has been discussed in details in this beautiful and deep paper of '96 by Balazs and Boros, and I suggest if you're interested in the model. Now, how I'm representing it now, because of Hilbert theorem, the pseudosphere cannot be globally embedded in a 3D Euclidean space, but a Minkowski space, where it appears, as in this plot, as a one sheet of a two-sheeted hyperboloid. And a first obvious reparametrization is in terms of pseudospherical coordinates that leads to the following metric. And now, from the polar coordinates, one can typically deduce a different parameterization that sometimes it's more useful for calculation, which is the hyperbolic plane or the Poincaré disk, that here I'm representing it with this tessellation by Escher of the hyperbolic plane. Now, the chaotic motion on the pseudosphere appears, so the pseudosphere actually extends to infinity. So here I'm plotting like this, but you have to think that contrarily to the standard sphere, this is unbounded. But chaotic motion arises for closed surfaces. So what Balazs and Boros do, they basically put periodic boundary conditions and they identify chaotic behavior. What we want to do is that we close it by gluing on top of the pseudosphere. So we cut basically the pseudosphere. We construct a cone, and then some tau x, dimensionless variable tau x, and then we add a cylinder on top of it. And the reason of this choice is that we really want to see what's the effect of the curvature. So in this class of systems for free dynamics, all the chaos is coming from the negative curvature, and we want to identify really what are the mechanisms linked to this curvature. So here I will have non-chaotic dynamics in the cylinder and chaotic dynamics in the pseudosphere. Okay. So in this tau model constructed in this way, we have two parameters, tau x and tau l, which are basically identifying the size of the volumes of the cone, the chaotic region over the total one, and we can choose sufficiently large parameters in such a way that we are aware that the model is always large, so we can always overcome the first quantum effect, which is when the de Broglie length is of the order of the system size. This is very large. And this will be, so this is basically, we are sure that the Ehrenfest time is very big. Okay, now I want to convince you that this model is chaotic, both classically and quantum mechanically. So the first thing that we do that one can study is the classical limit. So I have inside the cone this Hamiltonian, where I phi is the angular momentum, and in the cylinder, the system just moves on lines. And so in the chaotic, in the cone, in the hyperboloid, actually geodesics separate exponentially fast in time with a Lyapunov exponent that has exactly the scaling I introduced you before, so it's square root of the energy. Now, as an accident of two dimension, this specific model constructed in this way has also conservation of the angular momentum. So it's not chaotic actually. So geodesics separate exponentially fast, but then they hit on the top of the cylinder and they come back close, and they're close enough. However, it's exponentially unstable in the sense that because of this exponential separation of the geodesics inside of the chaotic cone. If I add an infinitesimal small perturbation, I will make the system chaotic, some sort of Loschmidt-Echo. And this is indeed what we do. So we can choose, we add the perturbation whose nature is not important. We check that it's irrelevant. And we choose the perturbation strength sufficiently small. And this is what we find. So the model is chaotic. And here I'm depicting the Poincaré disk, where the trajectory, so the geodesics appear as orthogonal circles. And indeed, by adding a small perturbation, you see that basically what I'm seeing is some sort of chaotic billiard on this Poincaré disk. Then we check that the perturbation is irrelevant, that the late time distribution is the equilibrium one, the system is ergodic, etc. And we also want to see that the Lyapunov exponent is the one that we expect. So in particular, since I have a region which is chaotic and a region which is not, the total Lyapunov exponent is going to be given by the classical one, and then I have to multiply by the ratio of times that I spend in the chaotic region over the total one, but because of ergodicity, this is basically the ratio of volumes. And what I check to extract the Lyapunov exponent is some sort of equivalent of the OTOC. So I'm looking at the Poisson brackets between the radial coordinate at time t and the radial coordinate at time 0, which is equivalent to derivative of the coordinate with respect to the initial momentum. So I'm doing the game backward. But what I want to see is that this object grows exponentially fast in time, and in particular that the rate of this growth is exactly given by twice the total Lyapunov exponent that I'm expecting. And this is indeed the case. So now I have full control on this toy model that is chaotic and it's doing what I would like it to do. And of course, now we want to go to the quantum solution and to the quantum problem. So what we have to do is that we have to solve the Schrödinger equation, and in particular, without perturbation. This is an exercise of quantum mechanics. So I have the Hamiltonian, which is the Laplace Beltrami inside the cone, and has the standard. It's a free Hamiltonian in the cylinder, and you can solve it exactly and write it in terms of Legendre polynomials. And then what we can do, we can add the perturbation and basically study the chaotic dynamics. So the first thing that I want to show you is that if I go on that side of the plot, so for very large energies or very large energies where the classical limit is expected to hold, I indeed find the chaos that I would like to find. So in particular, what we study is the microcanonical square commutator, in complete analogy to what I showed you before. So what I'm taking is the commutator between the operator at time t and the operator at time 0, and then I'm not averaging it over many initial conditions, but now I'm considering only for one specific eigenstate, which is at sufficiently high energy. And what we find for different eigenstates is that this microcanonical square commutator, indeed, it grows exponentially fast as a function of time. And the Lyapunov exponent is again exactly the one that we expected, evaluated at the energy. So this is this small h and 0 indicates the microcanonical, not the rescaled energy eigenvalue, and here it's growing exactly with the square root basically of the rescaled eigenvalue energy. So this is we are exactly in the situation in which the system classically would like to violate, because the Lyapunov exponent is scaling with the square root of the energy. Therefore, now we can see what is the quantum effect which wants to somehow impede this growth to be too high. And the first mechanism that we find is somehow a mechanism of intrinsic quantum nature, and it's related to a very interesting effect that the curvature itself is doing at the quantum level. So to summarize, it's basically what we will find is that the Laplace Beltrami operator yields an effective potential, which is proportional to h bar squared, that depends on the curvature. And the way to see it is basically you start from the Schrödinger equation and apply the Laplace Beltrami not for these, not for the this wave function psi, but for the one that is properly normalized, because usually you have to, the normalization comes with the square root of the determinant of the metric. So once you apply it, once you write it in terms of the transformed wave function, you find the following thing, that this wave function obeys a Schrödinger equation where the first term is purely classical. So this is exactly the same classical Hamiltonian that we have seen in the previous slide. And then there is a quantum potential that is proportional to h bar squared. So here I'm just dividing it here. And then on two-dimensional surfaces for radial coordinates, this is equal to minus k over 4, where k is the curvature of the system, and then a term that depends on the logarithm of the determinant of the metric. Let me mention that this kind of effects, so the fact that the curvature can induce kind of potential was a topic of discussion in the 90s, where people were looking at particles confined on a surface. They were not discussing in particular, at least as far as I know, negative curvature and not in relation to chaos. But this is something that was well known, that curvature at the quantum level induces potential, which can be attractive or repulsive. Now, in particular, so here I'm writing it in a generic way because K, which is the curvature, can be either positive or negative. And in general, if the curvature is positive, then my potential is going to be attractive. However, if the curvature is negative, which is the case we're interested in, because the negative curvature is giving us the chaos, what I'm finding is that the negative curvature is generating a potential which is repulsive. So what I'm saying is that the negative curvature, which is responsible for the chaotic behavior at the quantum level at very low energies, is also generating a potential, which is basically a step function, which is repulsive. So that wants to repel the particle from the most chaotic curved region. And indeed, so this is just a sketch, but as I told you, one can compute the eigenvalues and the eigenvectors of this model carefully, and from the exact wave functions. So here, this is again the rescaled, the dimensionless eigenvalue. So here I'm taking a very high dimensionless eigenvalue Hn, and I see that basically the wave function for zero angular momentum is completely delocalized over. So here in orange, I'm representing again the cylinder, and here in blue, I'm representing the chaotic region, which is the cone. So at sufficiently high energy, I'm completely delocalized over the two. And in particular, it's hard to see, but the quantum solution inside the sphere reproduces the WKB, so the semi-classical approximation that I know it should hold. On the other hand, when I decrease the energy, so and here I'm considering a dimensionless energy, which is really here, just below this gap, 1/4, so 0.24. What I find is that in the cylinder, the particle is still oscillating. So somehow I'm still, the de Broglie length is still small compared to, so I'm still somehow in a good classical limit, semi-classical limit. However, the chaotic region, so the blue region, is somehow acting as a step function. And indeed, the wave function is exponentially damped inside of the chaotic region, so I'm seeing only a remnant of an evanescent wave of something that doesn't want to enter into the cylinder. So how is this related to chaos? Well, if we acquire what we call a semi-classical perspective, in the sense that the system is large enough such that it's basically a particle inside the cylinder, but then it can also go, so I can treat it as a particle, but it can go also at sufficiently small energies in such a way that it can see now this big delta is a dimension, it's the gap that is proportional to h bar square. So I'm using this approximation in which I'm a particle, but I can see an energy at order h bar square. So the idea is that basically my particle coming from the cylinder will see this gap and it will slow down. So the velocity inside of the chaotic region is going to be equal to the square root of the energy, so proportional to the square root of the energy minus the gap itself. So the particle is slowed down. And if now I plug this velocity inside of the dimensional analysis for the Lyapunov exponent, I will find the following thing, that basically, if I go at sufficiently high energies, I'm not seeing the gap. So the dimensionless Lyapunov exponent is again 1 over square root of energy. But when the energy becomes comparable to the gap, I'm going to see its effects. And in particular, this is the Lyapunov exponent is going to vanish exactly at the value of the gap. Now here I'm just rewriting things in terms of the dimensionless variables. So I really have that for the dimensionless energy, when the dimensionless energy is very big, basically I just have the result in the absence of the gap. So the classical result, the Brody length over R. But when I'm decreasing the energy, basically the presence of the gap is bending the classical curve, and then it will vanish at small energies. And in order to corroborate somehow this picture, what we do is that we compute OTOC when the energies are just below, this gap. What's important is to make the system large enough in such a way that I can take eigenstates which have a sufficiently high quantum number, so such that they are indeed semi-classical. But you can see here, especially in log-log plot, this is a power law, so there is no trace of exponential growth. So summarizing this second effect that we're finding that really concerns this quantum effect of the curvature itself, is that basically the negative curvature, which is responsible for chaos at the quantum level, it's repelling the system from the most chaotic region, And with this approximation, what I'm finding is that Lyapunov exponent doesn't violate the bound, but actually vanishes at small but finite energies. So then we asked ourselves, okay, but what are the conditions for the bound to vanish up to 0 energy? So in the limit that people are actually interested in. So for vanishing temperatures or energies. And we will construct another like toy model or example in which we imagine that the system now has several regions with negative constant curvature. So imagine that now I'm constructing a cone with a given curvature, and then a cone which is a bit less curved, and then I have this hierarchy of cones that at the end they become a cylinder and they become flat. So here I'm representing it in this way. This is the radial coordinates. I have all these radius, small radii, and here is the smallest. And the Lyapunov exponent is going to be larger the smallest the radius of curvature is. So when the radius of curvature is small, it means that the region is very curved. So there are all these details, and indeed, as one can expect, higher Lyapunov exponent correspond to steeper details. However, this is the most chaotic region. However, this is also the region which has the higher gap. So the most chaotic regions are the ones which are associated to a higher gap. So what happens if I'm coming from high energy? So from the classical result, so from here, what I'm doing, the first region to get expelled due to quantum effects are the regions which are associated with the largest Lyapunov exponent. And therefore, this is true up to zero energy. So what I'm saying basically is that at zero energies, the bound to chaos is going to be dominated by the longest length scale, longest chaotic length scale in the model, and therefore it shall be a purely collective effect. So from this kind of toy model, we understand that if a bound to chaos has to exist up to the lowest energies, it's going to be determined by somehow the long wavelength effects. So it's a collective one. And again, this is a plot, but we can basically solve this toy model with all these different curvature, constant negative curvatures. So here I'm showing you an example again of the exact wave functions. And when I have two different cones, so two different pseudospheres with two different radius of curvature, and a cylinder. So the green is the cylinder, and these regions are associated to the most chaotic one and then the second chaotic one. And as you see, when I decrease the energy, so here it's an intermediate energy between the first and the second gap. The first region to go is the one associated to the smallest radius. And then when I go to very low energies, the system is repelled by the curvature and only will spend time where there is no Lyapunov exponent at all. So this is somehow the picture. And this is somehow the main effect that we identify. And another question that you might wonder is what happens if I don't have a gap. So one can imagine this situation either by applying somehow a gap on the cylinder, so forcing the system to stay all over the place, or to imagine that I just have a hyperboloid and then I cut it. So I just add a strong wall on top of it such that there is only one region of curvature, so it cannot repel the particle anywhere. So this somehow was one of the most complicated. We remain stuck on this issue for a long time, and then we tried to really isolate what the possible contributions were. And so the idea is that now we forget about the cylinder, so we only have this pseudosphere, and what we look. So we think classically. What would be the Lyapunov exponent of a particle there? So we look at the derivative of the length to respect to the initial condition, and in this case, it's dominated by the hyperbolic sign. So in this case, chaos is geometrical. So in this kind of models that we're considering, and indeed, it's basically coming from the fact that lengths are computed according to the correct metric. And in analogy to what we compute classically, we consider the following square commutator. So it's the expectation value of the hyperbolic sign, square, and then this other term. And then if you do the calculation, you see that basically these have a very different scaling. So we can estimate how this object is going to grow by computing the expectation value of e to the 2 tau over r. And now what we do in the simplest really trying to identify what's the simplest mechanism is to initialize a wave packet with an initial width, which is a sigma 0. And then we compute this is a Gaussian integral, we can solve it exactly. And what we find is the following result. So there is the center of the wave packet. So this is an exponential. This is the center of the wave packet, which is growing with the classical Lyapunov exponent t. So this is exactly what we would expect. However, quite surprisingly, there is somehow a regime which I have, I don't have a suppression of chaos, but actually I have an enhancement of chaos. And this is a super exponential growth. And this somehow always defines a time scale after which the exponential regime is actually overcome by the super exponential growth. We can define an approximation to make this length scale very large, which amounts in taking the wave packet very, very narrow. But then, even if we take the wave packet to be very narrow, we will always have that in order to ensure that there is somehow a Lyapunov regime in which I can see this exponential growth, I will need I will need the de Broglie length to be much larger than the individual, than this radius of curvature. So somehow I reobtain that in order to see this exponential growth now, so in order for the Lyapunov regime to be defined at all in the absence of several curvatures, I will need the de Broglie length to be much larger than R. And this somehow, it's kind of, it's not saying that there is a mechanism which is implementing the bound. I'm saying that there is an absence of a Lyapunov regime. And this was fine for Loschmidt-Eckos in a, this super exponential growth was fine for Loschmidt-Eckos in a very different context. And we were a bit surprised to find it also here, but this is what we have. So it's basically this third mechanism coming from the spreading applies when I do not have several regions with different curvatures, but when I'm constrained to be only in the pseudosphere, basically it's going to be the Lyapunov regime not to be present. So it's even the application of the bound, which is ill-posed. Okay, so I guess I'm right in time. Let me conclude, and I will hope that you will bring home with you at least this plot. So I hope I convinced you that dynamics on curved manifolds can give us many insights, and in particular on manifolds, the bounded quantities, so that not the bounded quantity, the dimensionless bounded quantities are only function of the geometric length scale over the thermal de Broglie length. And in these systems, classically, one has a violation of the bound, and this was indeed found in interesting many-body classical systems, and therefore one wants this classical violation of the bound is actually quantum mechanics acts against it in different ways, like trivial system size effect, some absence of Lyapunov regime, or this very interesting fact that the curvature itself is acting as a repulsive potential. And then I also told you that in order for the bound to hold up to the lowest temperatures, one really needs a presence of a hierarchy of length scale in such a way that the bounds at the lowest energies is going to be dominated by the longest length scale, so it has a true collective nature. And of course, as I told you, our things in line to do concerning this kind of approach is to go to macroscopic systems and to study spin liquids or hard spheres. And with this, I thank you, and I'm ready to take your questions.